Okay. Yeah. Welcome again to this topology and geometry seminar series. So today, David will continue his seminar series on the first encounter with diffeology, and he will be talking on higher and infinite dimensional structures in geometry. Yeah, over to you, David.
Yeah, thank you again for the introduction and as always for the invitation. Uh, right, so last time we introduced diffeology, and this time the title's even more ambitious, higher and infinite dimensional structures in geometry. So I won't claim to be able to give a comprehensive overview of both of these things. But the point is that diffeology doesn't quite stand alone. Uh, what we'll see here is that it relates to other structures that you may or may not have seen, um, which are meant to handle either singular or infinite dimensional situations. Um, and but before we do that, let's recap uh, where we are. So last time we had diffeology, or the category of diffeological spaces, like that. And again, so the point is that this is a flexible category where you preserve some notion of smoothness, but you now are able to apply this to a much larger variety of spaces. In particular, the category is complete, which means that it includes all subsets, or put precisely, the subset of a diffeological space, in particular, say, of a manifold, naturally inherits its own diffeology. It is co-complete. So that would mean that it includes all quotients. And again, this would mean that the quotient of a diffeological space also inherits its own natural diffeology, regardless of what the quotient is. So there's no condition on the quotient in order to get a diffeology. It just has one in any case. And it's Cartesian closed. And so this one would mean that it includes all function spaces. But I'll say mapping spaces, sorry. And the topic for today is going to focus on these last two, uh, because in these last two, there's some, more popular ways to handle these spaces. So, for example, quotients can also be handled with Lie groupoids. And I'll introduce what those are. And Cartesian closed, so the mapping spaces, well, there's infinite dimensional geometry. But here, what I'll mean by that is the closest analog to diffeology, which would be convenient manifolds or convenient calculus of Kriegel and Mihor. So, yeah, today we will introduce these two and see how they relate to diffeology. The point won't be that they're the same or that they're drastically different, but rather they overlap. And in some places, you might want to use groupoids, others diffeology, others convenient analysis. Okay, so that is where we stand. And now I will give a brief reminder on what diffeology is, because possibly you've only seen it from last lecture for about an hour. So a reminder is that I guess an object of the category of diffeological spaces. So a diffeological space is a set equipped with a structure called the diffeology. And I'll try and use the script D for that. And the nature of the structure is that it assigns to every open subset of Euclidean space a collection of plots. So it would look like this. du is a subset of maps from U to X. for each U subset Rn, and also for each n. So again, we're not restricting to some dimension here. We're taking all open subsets of all Euclidean spaces and specifying a distinguished collection of maps into X from those sets. And that's the D sub U. And so here, the members of this are called plots. And I didn't dwell on this too much last time, but I would like to write it again because I think maybe to some people this made a bit more sense. So equivalently, and this also now will include the axioms. I guess here I didn't rewrite the axioms of diffeology. I just said what it is, what kind of object it is. Equivalently, this D is a sheaf on the site of Euclidean spaces. So that would be like Euclid here, Euclidean. So the objects are these open subsets of Rn for all n. So is n bigger or equal to 0. And the morphisms are smooth maps in the usual sense for subsets of Rn. But this, as written, is not quite correct because diffeology, we want to always have a coherent underlying set. That's why the definition can start with is a set equipped with a structure. And if you just have a sheaf on some site, then you may not necessarily be able to recover some underlying set for that. So here, there's this technical condition that I won't dwell on, but we would put concrete sheaf, which is essentially to say that there's an underlying set of points, which sort of you can view the sheaf as being a structure on that set. Okay. So this is just a quick reminder of what diffeology is. To tell you what a diffeology, to specify diffeology, I have to specify these D U's here. And now let's start working towards the Lie groupoids. And again, this is in quotients, so I would also like to remind you the quotient diffeology. And here I'll just do it for a manifold, because Lie groupoids will be equipped to deal with quotients of manifolds and not necessarily of non-manifolds. So let M be a, and here I always mean smooth finite dimensional manifold. And let's take some equivalence relation without any assumptions on regularity, or it doesn't have to be a nice relation in any sense, just some equivalence relation. Then we always have a diffeology on the quotient. And to specify it, I have to tell you what the plots are from each domain U. And so this is defines equal, really. The collection of maps such that, so what should smoothness, sorry, these need to be into the set we're looking at. What should smoothness be? Well, smoothness is detected by smoothness in M, in the meaning that you have to lift up to M smoothly. So for every point in U, there exists two things, I guess. There exists a neighborhood of that point, and there exists some smooth map into U from defined on that neighborhood such that this commutes. So if that's the quotient projection here, that's your smooth map that you have from the assumption, and here is P restricted to V. Oops. All right, so let's tidy that up a bit here. Okay. So the idea is that you have a map into this quotient space and you declare it to be smooth if it lifts smoothly up to the space before the quotient. Okay. So this can always be formed given any equivalence relation. And so this is another way to say that every quotient space has a natural diffeology associated to it. Um, the reason, we have to take neighborhood, for every point, there's a local lift. There's sort of two reasons to motivate that. Um, you could say we don't expect maps to have global lifts generally. This is not something that we see very often. But also, we need to satisfy the sheaf condition. We need to satisfy the sheaf condition. And so this is what lets us do that. Okay. And then we had some, we could characterize the quotient in certain cases. And this, again, will prime us to work towards Lie groupoids. So we had the following results. Some of them, one of them will be new actually here. Uh, if you rotate the plane with an angle 2 pi over m, then these two quotients of these uh, rotated planes, these are equivalent diffeologically if and only if m equals n. And remember, the quotient topology, which is also the underlying D topology for the diffeological space, these are all homeomorphic for any m and n. So we're seeing some more refined information here in diffeology. We see the stabilizer of the action, I guess, Zm. And a similar example,
So
I
here,
can,
V
yeah,
is the neighborhood in U or in Rn?
here the neighborhood of U. Thanks.
Okay.
A neighborhood in U of R. So of course, U is also always a subset of some Rn in any case. But yeah, V has to be inside U. Okay, so yeah, these orbifolds, we see that m equals n is the is we can detect the stabilizer with diffeology. A similar example would be these spaces, which are not orbifolds. So if we act by the orthogonal group on Rn and on Rm, then in both cases, when we visualize them, we sort of think it's a half line because we have, these concentric circles. These are the orbits of the ON action or concentric spheres, and then they're parametrized by a half line. Um, but diffeology does not just reduce them to a half line, it actually sees the dimension of the space you acted on. So this is if, whoops, do this color here. Again, if and only if m equals n. And the last example, this was new, I guess, today. And the last one we all saw again last time is if we take these quotients. So for alpha and beta, here, these are isomorphic if and only if alpha is related to beta via homography, GL2Z here. Despite the fact that topologically, when alpha and beta are irrational, these have coarse topology. The only open subsets are the whole thing or nothing. So topologically, you can't distinguish these, but diffeologically you can. And in fact, that's true for all three of these examples. Topologically, they're indistinguishable, but diffeology is seeing some remnants of the original actions. Okay, so Lie groupoids will ultimately reproduce this, but from a different perspective, from the so-called higher categorical perspective. So let's now actually get to Lie groupoids. Um, so this is going to be Lie groupoid approach to quotients. And we'll begin with the motivation. So Lie groupoids sort of are going to generalize Lie group actions from our point of view. So we could say that if I want to handle these quotient spaces, then I can sort of think of the action. And then I could talk, for example, about equivariant maps between two group actions and sort of use that as some stand-in to move around different representations of the orbit space by having different actions that give the same orbit space. But there's also many quotients here. I didn't write them, but there's many quotients that don't come from group action. In fact, here will be one more that I'll add to this example here. So we have, this is sort of a non-group example. Uh, we could have a cover of a smooth manifold. Then how do I get the smooth manifold back from a cover? Well, I can take the big disjoint union of the cover and then identify 2 points when they're in the same set. And this is how you would form a general manifold by gluing open subsets of, say, a fixed Euclidean space, right? I would just take a big disjoint union of all my chart domains and glue points when the charts identify them. So, but if I work inside the manifold M, then the identification is really equality here. So we have this union here, the big disjoint union of the sets UI, and I can modify the equivalence relation that X is related to X. But I guess when I take the disjoint union, I'm tagging the X with the set it's in. So like Xj is related to Xi. So we generate the equivalence relation like this. And this thing here, of course, will be diffeologically diffeomorphic to M. Although this statement now has some content because the left side has a diffeology given by this quotient diffeology here, and we have the relation here. So you would have to do a quick check that you have the exact same plots that M does for this quotient. Okay, so here's an example of a quotient not coming from a group action necessarily. And so the groupoids will generalize group actions in a way that also accommodates things like this covering. So this is what I wanted to say. The groupoids motivation is that I would say local symmetry. They axiomatize local, the notion of local symmetry. And this is sort of a vague sense of what I mean here. So if we have, for example, a Rubik's cube, then we can model, solving the Rubik's cube with groups, right? So I can rotate one of the faces, I can rotate it again and again and again, and then I'm back to the original configuration, or I can rotate front face or the top face. And so we have a group action. And at any given configuration of the Rubik's cube, I can do any of my rotations. So the group is really acting on the space of configuration. There's a group action on the space of configurations. So here we have a group action. But there's other games out there, and some of them you need to keep it track of the configuration for your symmetries. And so this one would be, for example, the 15 puzzle. And that one here, if you don't know what it looks like, I'll draw the 9 puzzle instead of the 15 puzzle. You would have some numbers here, 1, 2, 3, 4, 5. And there's an empty tile, and then these are sort of slidable. So what you can do is you can take this tile here, for example, and slide it down here, or I could take this, and then I could take this tile and slide it here. And as you slide around, well, your goal is to arrange the numbers in order. But we see that if we wanted to model this with a group, we'd run into trouble because I have, for example, the action of moving a tile down, so I can move this tile down, and then I could move this tile down. But now I can no longer move any tile down, right? So move down is not an operation that I can apply, recursively forever. Here, now I can only move 3 to the right or 1 to the left. So what I can do in this game depends very much on the specific configuration of the board, unlike a Rubik's Cube, where your allowable moves don't depend on the configuration of the cube. So we need to sort of have some symmetry, right? I mean, I can move down, I can move back up. That's sort of group-like action, but I need to keep track of where I am in the configuration. So that would be having local symmetry, and indeed the algebraic object that captures this thing is a groupoid. Of course, these are very discrete situations, so there's no Lie really that the smoothness isn't quite there. So this is the kind of thing that we are going to define, something that can handle the symmetries of this type of puzzle. So here we go with an actual definition. a Lie groupoid is a category. So a category has arrow morphisms and objects. And now in a general category, the morphisms are not always invertible. So here we're going to require that. So every morphism is invertible. And here, when I say category, we shouldn't think of categories of mathematical objects. So I'm not thinking of the category of vector spaces or the category of smooth maps or the category of diffeological spaces for that matter. Here, the set of points in M are going to form a manifold. So it's a very small category. Um, and the categorical structure is really just going to give us this notion of symmetry. We're not, again, talking of a category of spaces of some kind. So a Lie groupoid is a category such that every morphism is invertible, and G and M are equipped with smooth manifold structures. And then, of course, if we do that, then suddenly all these structure maps in the category should be smooth. So we have manifold structures on the arrow space and on the object space, and everything is smooth. And a Lie groupoid has a second condition, which maybe doesn't look quite as natural. So here, right, these conditions sort of say, okay, it's a groupoid that is smooth. But there's an extra condition here for the groupoid, which is that we want the source map and the target map need to be submersions. So I should but furthermore require that the source and target are submersions. Sorry, let me put that here. Require the source and target to be submersions. Um, and I'll explain what the source and target are in a second. Uh, okay, so this is going to be our definition of Lie groupoid. Now, the manifold structure on G may not need to be Hausdorff second countable. I'll say that here, but I'm not going to dwell on that slight extra generality that we can get. Okay. So in detail, what do we have from this structure? What does saying a category give us? So saying that it's a category immediately gives us a bunch of maps. So it gives us a map source, write down the name, S from G to M. It has target T from G to M. And those tag basically where the morphism starts and ends in G. And then we can multiply which is like a composition. But just like two maps, we can only compose if their codomain matches their domain. Here, two arrows can only be composed if their source, if their target matches their source. So we need a fiber product for the domain of the multiplication. And here we'd really like to write without writing the M, so just GH for the multiplication. You have the unit, which is like the identity. So this goes the other way and sends you to the unit arrow. And we have inversion from G to G. That one here is groupoid specific. In a general category, of course, you don't have an inversion map because not every morphism is invertible in a general category. So here we have the structure and the picture, one picture for the arrows at least, is that we'll think of arrows maybe like this. So G is in G, and it goes from one point in M to the other, and G is sort of a local symmetry of the manifold. So given a specific groupoid, we're saying there's some kind of symmetry that takes X to Y, but we don't require that G be a Lie group element or anything like this. So we're not imagining G acting on the entire manifold. So in this 15 example, for instance, you would have an arrow from this configuration here. This would be like an X, and then this configuration would be Y, and the arrow would be the movement that takes two up to from here to here. And this arrow only does this. It does not, affect any kind of other motion here. So this would be a different arrow to go moving the five up. It would be a different arrow because it has different domain and source and target. Okay. So this is the data of a Lie groupoid. And there's a picture we can sort of try and draw of the arrow space because the arrow space, remember, is a manifold in a Lie groupoid. So we should be able to have some picture of it. So here you would have, say, well, let's say the image of the units, but really just think of it as M. And then you have two maps, source and target, and these are actually submersions. So in other words, they're fibrations of the space. They foliate the space with their fibers. And so you have the source maps here, which maybe has these kind of fibers. And then you have the target map, which would have this different color here. Here, I'll try and match up so they're intersecting. Of course, it's foliated the space, so I really need to draw infinitely many of these in a dense way, but just draw some of them. These could be the T fibers. And then you have an element G here, for example, and then its source of G would be down there, and its target would be there, because if G is in this blue target fiber, that means that the target is the target fiber over Y, so there's Y down there. So G has source X, target Y. Then you might also have some H with source Y and target Z. And then you can compose them, and the composition should go from X to Z. So here I would have, let me extend this a bit, HG. And in this picture, I can augment it to show the composition. You'd have some other arrow here. It must start where G ended. That would be H. And then you'd have the composition HG going from X to Z. Or the multiplication HG. Okay, so this is a little picture of a groupoid. Now, what are some examples?
Just 1 minute.
Yeah, yeah.
So I'm not understanding what is the meaning of GH in M.
Of which?
So when you define the multiplication, the fiber product on G and G
Yeah,
cross G, so
yeah,
it goes to M, but so
yeah.
G is
Oh,
a
wait.
group
Oh,
here.
no. Sorry, that's a bad typo. This is a bad typo. It doesn't. It has to go to G.
Right. Okay.
If that's the confusion, yeah, that is confusing. No, it's G. That's a typo.
Okay.
Yeah. Yeah. Sorry about that. Very sorry. So yeah, needs to be G here. Um, okay. Everything else is going the right direction though. Yeah. Right. So some examples of these. Uh, if G is a Lie group, then we get, well, okay, so here, so G normally is the space of arrows. So maybe I won't quite use G again, at least for these examples. I'll say like H is a Lie group. Then we get a Lie groupoid over point. And to specify the structure of a Lie groupoid, I can draw what the arrows do, and I can tell you what the multiplication is. So an arrow, which is an element of H, is viewed as an arrow going from the point to itself. I'll write it down like I wrote it up there. So there's no objects to tag there's no real objects to work with. It's just this point. And the multiplication, G I guess M of GH is just a group multiplication. Okay. So a Lie group is a groupoid, but over a point. On the other hand, we can have a manifold without any sort of symmetry, without thinking of any symmetry of it. Then really we don't have any reason to connect any 2 points in M by anything. And we have this groupoid here, which is M over itself. So the arrow space is M, the object space is also M. And an arrow is going to be an element of M viewed as an arrow from itself to itself. So X in M is viewed as an arrow from X to X. And here the multiplication is that, well, you can only multiply arrows if their source equals their target, but everything is equal to X. So the multiplication is really X dot X equals X. So if in the first case, for Lie groups, we have a bunch of symmetries, but no underlying space necessarily, just a point. So only arrows. For the manifold here, we can also just say we have no symmetries and only objects. And then we have these two extremes. And we also have, of course, actions, because I said Lie groupoids generalize actions. So say I have a right action, then we get a groupoid with this structure where the arrow space is the product. And so how do we view elements of the product as arrows? So I'd have an element of the product here, and I'm saying this is viewed as an arrow from one point in M to the other. Well, here we actually have a global symmetry H. So H will take X to X dot H. And so that's how we view this arrow here. H takes X to X dot H. So in a way, we're taking the group action where H is acts by a diffeomorphism of the manifold and breaking it up into a bunch of pointwise information. Each point X is mapped to X dot H by H, and I add that to my data as this pair XH. So I'm taking this global information and breaking it up into a bunch of pointwise information. And the multiplication here, I think I would be as follows. So YG XH should be, well, if I start at X, I should continue to start at X, but instead I should go from X to X dot H like this, and then I should go from X dot H to G, X dot H dot G. So this is X dot H dot G, and it flips because it's a right action. And the only way this makes sense, because now I've broken up everything pointwise, right? I'm thinking of the pair as going from a single point to another single point. Then the composition now requires that the start of the second arrow must be X dot H, the target of the first arrow. Okay, so this is how you get a groupoid from a group action. And the last example will be a covering. This is to justify that, of course, Lie groupoids handle more things than just group actions. If they only handled group actions, then we should just talk about group actions. But they handle more things. So if this is a cover of M, then we have an associated groupoid that looks like this. So the objects are going to be the disjoint union, and the arrows are going to be things in the intersections here. So this is the groupoid structure. The objects are the disjoint union of the UIs, and the arrows are the disjoint union of the overlaps of the UIs, the intersections of the UIs. And the arrows will kind of look like the arrows up here, except now that we've taken some big disjoint union, the points in X are tagged with what elements of UI we're viewing them in. So which UI we're viewing them in. So we would have XJ and XI, and then the element XJI is viewed as the arrow between them. So if I have a point X as viewed in the open set UI, it's the same X as the one in the open set UJ. So I want to identify them. That's the symmetry of this disjoint union. And I do that by having this arrow XJI. And of course, if there was some K which also contain UK which also contained X, I'd have another arrow. And I can compose them using essentially a cocycle. So I won't write the composition here. But the point is that we have this groupoid. Now, Lie groupoids should, we want to use them to model quotients. Where is the quotient in this picture? Right now, we just have these groupoids. So the quotient is going to the orbit space. So every Lie groupoid has an orbit space, which is defined as follows. M1G. So I'll put it down here. Sorry, I need more space. And this is defined to equal M mod the relation X is related to Y if there exists some arrow G going from X to Y. And this is transitive because we can compose arrows. It's symmetric because every arrow is invertible. So symmetry comes from the groupoid assumption. And of course, it's reflexive because there's a unit arrow from every X to itself. So every Lie groupoid has an orbit space. And also, by the way, we can already equip this with a diffeology, and that's what we'll do. So the Lie groupoid itself could stand as some model for the orbit space, or the diffeological structure on the quotient will be a smooth approach to the orbit space. And now we're going to compare these two points of view. But maybe I'll just indicate in these examples what these orbit spaces are. So pardon that I'll add some lines here. So here, the orbit space, what should it be? Well, I glue 2 points in UI and UJ if they're the same point, but they're in the overlap of UI, UJ. In other words, I glue the UIs to the UJs on their overlap. That just recreates the manifold then. So here, the orbit space is going to be the manifold. Up here, I glue or I identify X with X dot H. That is simply taking then the orbit space of the action. So here the orbit space is M mod H. For the unit, for this trivial kind of groupoid, I don't identify anything, so I just get M back. And here, the point, there's nothing, the point is already a point, so I can't quotient it to anything less than that, so the orbit space is a point. And in this top example, we see that the Lie groupoid structure could be completely lost by taking the orbit space. I mean, if I have another Lie group H, I'll get the exact same orbit space over the point. So a Lie groupoid, in principle, can see a lot more than just a diffeological quotient. But then in other cases, it sees exactly as much as a diffeological quotient. And in fact, we'll highlight the first and fourth examples to see sort of an issue with this point of view. So here we say if Lie groupoids are going to be atlases for quotients, then shouldn't these two, the covering groupoid and the trivial groupoid, shouldn't they be isomorphic in some sense? So here we have a quick section. So this would be Lie groupoids as atlases. Sorry, Lie for quotients. And here's the issue. So observe that this groupoid and this groupoid, the covering groupoid, are not isomorphic as the groupoids. What I mean is that there's no functor. So of course, a Lie groupoid is a category, so at least the morphisms between Lie groupoids should be functors. And so there's no invertible functor between them. Um, so we do have a natural functor. This is not in a precise sense, just this is just in a vague sense. Natural functor, which takes, it just forgets that you took a cover. So it's really it's kind of like an inclusion functor. And I guess it does, it has to have a arrow component and a top component. So there is this natural inclusion functor where we just forget the I. So if X is a new I, we just map it to X. Um, and this is a good candidate for an isomorphism of these two groupoids. In other words, if they represent the same quotient, namely M, they should be isomorphic in some sense. But of course, it's not on the nose an isomorphism. So we need then a more general sense of when two groupoids are the same. Because these groupoids, should be quote unquote the same, or they should represent the same thing. And we could say they represent the same thing if they give the same orbit space, but the orbit space does not need to be a manifold. And even as a diffeological space, again, we don't want to say that all Lie groups are necessarily the same, right? Even though all their orbit spaces are the point. So here we will give a refined notion of equivalence, which captures sort of the transverse data. So I'll just say the remark is that we isomorphism. And this one will get a bit technical. So I think I'll say it just to establish that it exists, but then we'll understand it better by examples. So definition, a Morita map, that's the definition of this, is a functor. So now you have to forgive me using H for both the group and the groupoid. Now H is a groupoid over N, and the functor has two components here. So a major map is a functor that is essentially surjective, well, smoothly essentially surjective. So this is this fiber product here. So phi 0 goes into N, and T, the target for H, also goes into N. Sorry, this is fiber H. And then this map here is going to be this source of the projection is a surjective submersion. And that can be, at least the surjective part can be unraveled to say that for every object Y, there exists an object X. And, oh, sorry, I made a mistake. This is N. That for every object Y, there exists an object X and a morph and a arrow G, which does the following. It takes, and then I have to make sure I get the order right. Yeah. Sorry. Too many typos. Sorry. For every object in Y, there's another object in M and some arrow H in over N, which takes y to 5h. So this is the essential surjectivity from my category, right? Every object of y is isomorphic to some object that came from M using a specified isomorphism in H. And we also want it to be fully faithful. So says that this diagram here and this one is the pair of phi 0 itself, and this one is phi. That is a pullback. And there's a pullback in the category of manifolds. So what this one says, if you unravel it, at least for the pullback in the category of sets part, it says that if you have something in this pair, M times M, and you have some arrow in H that takes phi this would be phi 0, I guess. Sorry. Phi 0 of x prime to phi 0 of x, then there exists a unique arrow in G, which is sent there. In other words, phi is injective on the sets of arrows between two fixed points. So the sets of arrows between x and x prime biject onto the set of arrows from phi 0 of x to phi 0 of x prime. Okay, so this is essentially to say that a Morita map is more or less an equivalence of categories. And just like two categories are equivalent doesn't necessarily mean that they are isomorphic as categories. Here, two Lie groupoids, we already want them a notion of equivalence that does not require an isomorphism. So this is going to be Morita map. These will really be the equivalences for that help us use Lie groupoids as atlases. But there's a small issue. If it's going to give a notion of equivalence, it should be an equivalence relation. And for categories, to have an equivalence of categories might be an equivalence relation. But here, there's some smoothness going on. There's some smoothness here. And so we really don't expect to have, a a symmetric relation here. There might be a Morita map one way, but not the other. I mean, we can see this in the covering example. This iota is going to be a Morita map, but how do you go from M to the disjoint union of the UIJs? I can't even think of how one might do that in a well-defined way. So, not smoothly at least. So these are going to give we want these groupoids to be equivalent, but it's not an equivalence relation. So we need to make another definition. And we say that G is Morita equivalent, which I'm going to write ME a lot. If we have, or if there exists, not a Morita map necessarily, sorry, G is Morita equivalent to H if there exists. Not necessarily a Morita map between G and H, because again, that won't be symmetric if we say that's the relation. So there needs to be a third groupoid and Morita maps from that down. So these need to be Morita maps. Okay, so as soon as we ask for this triangle to exist, we can get a symmetric relation. So this is a definition of Morita equivalence. And it's weaker than requiring there be an isomorphism. In fact, we don't even require necessarily that there's any functor from G to H for that to view them as Morita equivalent. Okay. This is our bridge then to diffeology. So in each of the examples before, the diffeological Morita equivalence is the same as Morita equivalence. So examples would be that. Of course, now I'm not talking about the orbit space, right? I have to talk about the action groupoid. So this is the action groupoid. This is Morita equivalent to, sorry, I used M and N. And M, and that's a 2, if and only if M equals N, and ON is Morita equivalent to OM. Same condition. And then finally, this, these are different examples, Z plus alpha Z acting on R is Morita equivalent to Z plus beta Z acting on R, if and only if alpha is related to beta on GL2Z. And then the last one here, which is going to be not a group example, will be that this covering groupoid is Morita equivalent to the trivial groupoid, as we needed. Okay. And then finally, to end this section on groupoids, I'll give a sort of sense of when you have, what can sort of, what might generalize this type of phenomenon where the Morita equivalence is given by diffeological diffeomorphism. And then this will also say, for example, how orbifolds are viewed completely as diffeological spaces. Sorry about this. And so this would be a theorem. Again, so give the relation between Lie groupoids used to model quotients and diffeological spaces. So let's let gamma act on Rn. Okay, so we will assume that this action is effective. In other words, no two group elements induce the same diffeomorphism. So let gamma act effectively. Suppose one of the following hold. So gamma could be finite. Gamma could be acting affinely, or gamma could be countable, and it could be a subgroup of the affine group. So countable acting affinely. Or 3, gamma could be countable and a subgroup of the isometry group. G here could be any metric. It does not need to be the Euclidean. If it's Euclidean metric, then really we get a subgroup of the affine group again. So that doesn't help generalize, but here it could be any metric. Then, well, okay, so this is a gamma. Suppose that gamma prime is similar. Maybe on Rm. Then gamma acting on R. N is Morita equivalent, the action groupoid to gamma prime acting on M, if and only if Rn mod gamma is diffeologically diffeomorphic to Rm mod gamma prime. So here we see the Moritz equivalence is precisely the same as diffeological diffeomorphism, but we have these conditions, and these conditions are meaningful. So there exists countable group actions where we do not have this conclusion. There always is this implication. So a Moritz equivalence always induces a diffeological diffeomorphism. But there are two countable actions, which are not in those three examples, where you have non-Moritz equivalent groupoids, yet their orbit spaces are the same. Uh, and I should give some attribution here. So the case one is neater. Glacius de Moor and Lafreniere in, I think, 17. Case two, Glacius de Moor and Prato in 20. But then this was also treated in a more general way by Arson and myself in 23. And then the last one is myself in 24. So yeah, this is a relation between diffeology and the Moritz equivalence. I used to give, so again, there's example of a countable group acting effectively, which fails this theorem. I'll give a more simple example just to drive home the point that Moritz equivalence is not the same as diffeological diffeomorphism. Uh, so this one non-example here. You could have On acting on Rn, and this is not Moritz equivalent to SON acting on Rn, even when they have the same orbits of concentric spheres. So they have the same orbit space. But they're not Moritz equivalent. Of course, this does not really this is not a counterexample to the theorem because the theorem is having countable groups here, but it's the same spirit. Okay, and this I think wraps up what I wanted to say about quotients. So there exists these groupoids which model local symmetries, and we have a more flexible notion of isomorphism between them, and that more flexible isomorphism does let us sort of use groupoids to represent quotients. It's flexible enough to say that the covering is Moritz equivalent to M, uh, and then also all of these cases. But it is slightly more subtle than just diffeologically diffeomorphic, because we have, for example, ON and SON being distinct. Or, I mean, an even simpler example would be two Lie groups. These are Moritz equivalent if and only if ultimately they're isomorphic. Certainly, their orbit space doesn't tell you. And that wraps up what I wanted to say about the Lie groupoid side of things. So I see that it's been an hour, but I'm asked, so I'll ask, so again, yeah, do these go for longer or should I wrap up here? I don't mind if I should wrap up here.
Oh, it depends on you, but I do have one question here. Uh,
Yeah,
so 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 you have the condition effectively there. So
yeah.
like, is it like can we, if you don't have this action to be effectively, then also can we get uh this Morita equivalent if and only if this, or it's not?
Yeah. So if it's not effective, then I think so necessarily you will not be able to get to this same conclusion because the effective will mean that yeah, if it's not effective, you'll have two group elements doing that are indistinguishable from the point of view of the quotient. Two group elements that have the exact same affect the exact same diffeomorphism. Um, and one thing we should notice here is that the diffeological structure on the quotients, uh, that is not even sensitive to gamma, really. This is sensitive to the orbit partition. So if two actions have the same orbit partition, then the quotients will be diffeomorphic. That even goes all the way back up here when we look at the quotient diffeology. It only depends on this equivalence relation. So in other words, on the underlying orbit partition. Um, yeah, so if you don't have if you have a non-effective action, you'll never be able to recover that non-effective part from the quotient space. In other words, you're not going to get the Morita class back. What you'll get is only, the diffeology will only maybe return action, the effective part of the
Okay.
action. Yeah.
No, do you have a quick example of this one?
Of this equivalence, like
Right.
of
Where, no,
this,
if, yeah, right.
you're asking for a quick example of the theorem?
Right. Yes. Where, no,
Yeah.
I'm asking for a quick example of this theorem as well as if you don't have this effective, then the theorem is not true.
Uh, oh, hello.
Yeah. Am I audible?
I think my connection got a bit unstable. So you're asking for a quick example of this theorem as well as,
A non-example if I don't assume effectiveness.
right. Yeah. Yeah. So I think these examples here, so this one,
Okay. The first one. Okay. Right.
yeah, the first one, for instance, here's a finite group
Yeah.
acting.
Right.
And
Right.
also the second one is an example. This is the second one is an example of both two and three. It's
Hmm.
countable affine action. Because it acts by addition on R. So there's a countable affine action. It also happens to be an isometric action for the standard metric on R. Uh,
Right.
yeah, so those would be examples. Um, and a non-example for non-effective, uh, I'm sorry to give a silly one, but you kind of build them in the same way if you have H acting on the point. So this gives a Lie groupoid, which is just H over the point for H a Lie group. And I can also have
With a different.
this. And then
Right.
now this is an example because there's a fact, which is that H is Morita equivalent to G if and only if H is isomorphic as a Lie group
Mhm.
to G in this special case here. Yeah.
Right.
All right. So of course these are not effective. I know this looks kind of silly, but you can do the same thing with any group action on a manifold. I'm sure you can just add a spurious copy of some group that does nothing. And that would, yeah, yeah.
Okay. Thanks.
Yeah. Okay, so you said it's sort of my discretion if we go for 1.5 versus 1. Is that right?
Sorry.
You said it's my discretion if we go a bit longer.
It's fine, I guess,
It's fine. Um,
but it
maybe I'll
depends on
stop
you.
here.
So,
Yeah, maybe I'll stop here. I don't want to
okay.
tire people out. So we got to quotients,
Yeah.
and we'll stop. Yeah. So thank you.
Okay. Thank you. So, are there any questions for David? Okay, then let's thanks him, and we'll meet again on next Tuesday at the same time. Okay. Yeah.
Yeah.
Thank you, David. Bye.
Yeah. Thank you.